welcome in. When you are going to be sketching polynomials, or in fact any function that you are going to be given, so at some point probably in calculus you're going to be asked to do this without actual tools. So here's a list of things that you kind of can think about. So it's almost like a checklist to do, 1, 2, 3. So things to keep in mind. And what I'm going to be showing you here in this video is I'm going to take two examples. I'm only going to concentrate on polynomials in this example. I'm going to do other examples as well with possibly some other functions. Okay, so you're going to be able to take a look at that as well under my calculus playlist. So in our example number 1, okay, so I have function fx. It is constrained, so we have it constrained at least in this particular case. So it is constrained between -3 and 4. So that's what you see there on the screen. Maybe I'm going to use kind of yellow so that it comes up a little bit better there. So here's our constraint. Now, polynomials are defined on the entire x-axis, so it's basically for all of r unless we constrain them. So in this case, we are constrained, so we have endpoints -3 and 4, but the function is defined everywhere. So whenever it says, so for instance in here, it tells us, okay, so what is the domain? Well, our domain in here, so point number 1, our domain is basically restricted between -3 and 4 for x, right? And notice that it is -3 right here, but it is not equal to 4 right there. So we kind of have to be careful. So the first thing that I will notice is the following, that if I would draw this out for myself in terms of thinking as this is my x, and I know this is obviously going to be two-dimensional, we'll get there. But within here, I know the following. I know that this is constrained at -3, and then this is going to be 4. And now what do I do know is it includes, okay, the 3, but it does not include the 4. So if you recall, so the way that we would do this is, okay, so we would constrain it in this particular way, where we use brackets as so. So there is basically our domain. That's where the function is going to live. So that's step number 1. Now, step number 2, which you can see there, it states, find the vertical horizontal asymptotes. Now, having vertical and horizontal asymptotes definitely works, and we certainly have to think about it. But is that the case for polynomials, right? Vertical asymptotes means that the function is going to be approaching those vertical asymptotes, but it never gets there, which means it's actually not defined, okay, at some particular value of x. Now, that's not the case for polynomials, so we don't really have any vertical asymptotes. Now, how about horizontal asymptotes? So how about if you're going back and forth on the horizontal asymptotes, right? Are you approaching something? Well, again, for polynomials, so depending on what the order is, they're going to skyrocket for us. So if we didn't have the constraint between -3 and 4, then this function, if you take a look, so horizontal asymptotes, you can think about what happens as basically x approaches infinity and as x approaches -infinity. Well, if we take the approximation that it goes to infinity on the positive side, if we didn't have this constraint of 4, you will notice that this function is going to blow up on us, and that's what's going to happen with any polynomial. So any polynomial of order 2 or higher is going to be blowing up. I mean, in fact, even linear functions do blow up, okay, for us, because they just keep going, right? Depending on what the slope, of course, is, unless the slope is flat, it's just a flat line. So here, the horizontal asymptotes, are there any? No. So how would we check this? Well, if we had to check it and it was a non-polynomial, we would just simply say, okay, well, what happens as x is approaching to infinity on the positive side, and then what happens to x, okay, as x is approaching to -infinity? Well, in both of these circumstances, it's going to blow up, so that x to the 3 will dominate, and it will be kind of blowing up on the positive side and then blowing up on the negative side the other way if we didn't have the constraints. So in this case, We have no vertical or horizontal asymptotes. The next thing is that you see there, it says find any holes. Now, what do these holes actually are, right? Well, the holes, okay, with respect to a function means that it's not defined somewhere. But these are for kind of rational functions, once again, not for polynomials. So that's not going to be the case for us in here. Now, for those students, okay, so in terms of vertical, horizontal, and any holes, I'll put up a link up above there. It will bring you back. I talked about just those specific topics actually in advanced functions. So you can take a look at that just to refresh yourselves for calculus once you do start plotting. Now, how about number 4? So with regards to polynomials, can we have x-axis crossings, right? So this is the zeros of the function. Well, yes, indeed, we are going to be running into these, okay, possibly, depending on what the actual function is, but we can certainly try to see and test it. So these crossings, okay, that we have to set the function equal to 0. Now, this is annoying because now we have to solve this, right, for our 0. So if I duplicate this, I have to set this equal to 0 and then actually find out what these zeros or roots of this function is. For a polynomial, I mean, this is of order 3, so maybe it's still doable for us. But, order 4, order 5, and so on, if it is actually an expanded form, okay, then it's going to be a problem, right? And if a teacher gives you, orders, even if it's 3, okay, 4, 5, unless there's something you can spot very quickly on your roots, these are going to be problematic. So what I kind of envision, especially as you're doing your calculus for the first time and you're not supposed to use a tool to graph this, then it shouldn't be really of order 2, of order 3, okay, and then possibly order 4, but there has to be some kind of a hint or something that you can very easily find in roots. Okay, anything bigger, it gets hard. So that's just a heads up to students. Don't think that this is all going to be easy, because finding roots on its own is hard, unless you're using tools to find it, right? Which we certainly can on the internet, okay, or graphing calculators and so on. But in this case, I don't want you to use tools. I want you to really think of the steps that you have to take. So for instance, for this one, I mean, I can actually kind of see that, like, if I look at this, so this is a 4, I have a 3, so I would substitute, I would basically use the remainder theorem to try to see if there is a root that I can spot. And I can actually spot one, and I believe it's going to be -1. If I substitute -1 into this function, what you're going to get is so -1 cubed is -1, then it's going to be -3, because -1 squared is just 1, and then plus the 4, and indeed this equals 0. So I do have one particular root in here. So my root, okay, so I would have, or I could factor this out, so -1, so that means this is going to be that. Now, what you would have to do here, okay, is, again, if you're doing this from scratch, you're going to have to do now long division to try to factor this out so that you can see what is remaining here for this right there. Now, I'm going to do this in fast-forward fashion so that I can break this down. I can factor out this entire thing and then see and find my zeros, okay? So I'll be back and I'm going to do this long division. All right, so welcome back. So here you go, okay? So that is the kind of long division, so in terms of factoring. So basically what I have is this and this. Now, from here, it's actually much easier because I can spot here. So this is nothing else. This is just a quadratic. And I can see that this is a perfect square. So this is going to be x minus 2 squared, and then this is x plus 1. So now my zeros, well, my zeros happen at -1, and then from here I have 2 of them because this is of degree 2. Okay, so I have it at 2 as well. Okay, so those are my zeros. So now that I do have my zeros, okay, so those are the things that I found, in terms of the zero crossing. So that means these are the points where the function either crosses or touches the x-axis. So again, so now if I'm going to be going along here, so I'm going to take this, copy it, I'm going to bring it down for myself over here. So what this is now saying is, all right, so I have -1, so that's going to be somewhere over here, maybe -1. It possibly crosses or touches there, and then I'm going to be here at 2. Okay, and again, it either crosses or touches the x-axis, that the function that is. So now what I will do is, if you go back in here, so it says create test points to identify where the function is positive or negative. So that means we want to know where this function is positive or negative, meaning where is it above or below the actual x-axis. Okay, so when we're plotting it, so how would this look like? And how would you do that is you simply, now that you know that the function is this, and we have it in factored form over here, so what we would have is you can just find test points. So the test points that you use, it doesn't matter. So on the kind of left-hand side, so right here, so I guess between here and here, you can find a test point and then see what happens. You can substitute them in. Now, a good test point, I guess, it could be -3. You can substitute that, okay? Or you can put -2 in here as well. It doesn't matter. And is this going to be positive or negative? So you would substitute your test point, so let's say -2, okay, as a substitution, and then see where that function will be. Is it going to be above or below? So is it negative or positive? So if you're substituting -2, okay, what you're going to notice, it's going to be negative, right? You can substitute it. You can try that out for yourself. And then this, okay, is going to be negative, okay, between -3 and -1. So it's going to be below the x-axis. Now, between here, so you can find another test point. So now having between here and here, and this one is, the one that I would probably pick is 0. I always like picking zeros if I possibly can. So within here, so if I'm going to be picking, so 0, so let's say it's somewhere over here, if I would substitute that in there, this is going to be actually positive in here. So if that's going to be my test point right here, so that's my other test point, so it looks like the function here is positive. So it's going to be above the x-axis. And then between 2 and 4, so again, you can now substitute right here and then see for yourself. This isn't really proportional. 2 and 4 are too close together, but that's okay. So within there, if you substitute, for instance, 3, so within, so this can be your test point. Now that 3, as you substitute it in, again, this looks like it's going to be positive, okay, above here. So just from this information, you already know that the function is going to be below the x-axis between -3 and -1, but it's going to be above, right, for the entire duration, except at 2, where it's equal to 0. So that means it actually never crosses through 2. So it looks like it touches. It's probably some kind of a local minimum, I would guess, right? We're going to be able to find that out, but that's exactly what it would be. So just from this, I can already kind of picture how this would look like. Now, we can keep going to make this more and more accurate. So we're going to keep this. So this is now, we know all the information where the function is positive or negative. So there you have that. Now, next, all right, so if we come back here, now we want to find y-axis crossing. Now, there could only be one because it's a function. So you can't have 2 points where it crosses the y, which means the vertical axis, because if it did, then we don't have a function, and polynomials are certainly functions. So this is now looking at the actual y-axis. Now, y-axis means x is equal to 0, so that's the easiest one to do, because you can just substitute into your function 0 and then find out. So notice that, this is going to be 0 and this is going to be 0. So basically, it's 4. So it crosses the y-axis at 0, 4. So now we know the point where it crosses that. So what we have, so now if I kind of skim this down all of a sudden, and now I create a vertical as well. So, I can kind of try it in this way. Let's see, so that's that. So that means, let's say if this is 4, it means the function is actually crossing through here. All right, so that's what it's going to be, crossing through. So that's my y crossings, right? I know my endpoints, -3, 4. I know the 0, okay? So I have 1 crossing, and it looks like I have 1 touch at 2. That's what I have so far. And now I can kind of just keep going. So, what else do we have in this order to do? Now, find the critical points. Well, what are critical points? So if you forgot about that, I'll put up a link up above there. So, we studied that in calculus. Critical points is where the derivative is 0 or it doesn't exist. Now, in this case, it's a polynomial, so it's very well behaved. Now, where does the derivative not exist? It actually does not exist at the endpoints, okay, right here. So, we're going to be kind of checking those critical points. We can put those values in exactly to see where that function will be ending. Now, why doesn't the derivative exist there? Again, okay, that is because from the left-hand side on the -3, we don't have a limit, right? Because the function is not defined to the left of -3. And then the same thing at 4, from the right-hand side, we don't have a limit. So we can't really have a derivative there that exists. Now, we can substitute these two values into our function and find out what they're going to give us. So within here, so let me just substitute. I'm going to copy and substitute these two endpoints. And then I'm going to also substitute, okay, where the actual first derivative is equal to 0. And I'm going to take the derivative in just a moment. Okay, so I'll be right back. All right, so here you go. So those are the endpoints from -3 and 4. So I just substituted all that back in there. Now we have those values. Now the other critical points, okay, so we have to take the derivative. Okay, so the other derivative that we're going to get is going to be 3. This is x squared minus 6x and then 0. All right, so now I can actually simplify this. This factors out pretty nicely. So 3x, take that out. This is, I guess, x minus 2. Okay, so that's my derivative right there. Now, where does it equal to 0? Well, it equals to 0 at x is equal to 0. And I guess from here at x is equal to 2. So those are the 2 points. So basically what this is telling me, the slope is equal to 0. So slope is 0 to 0 right there. So now we have allocated where those 2 points are. Now, let me just kind of substitute. Now, I actually already know x equals to 0. That's, the crossing through the y-axis, right? That's where it crosses. So that one we've already found. And then x is equal to 2, we've already also found. Okay, so that was where we had the y. It wasn't a cross, sorry, the x. Okay, it touched the x there. So there you go. So if I go back in here, so what it looks like, basically it looks like, there's a 0 in here. Now, we'll find out if it looks like this. Now in here, it definitely is going to look like this. It's going to touch because of the fact that my function is positive and positive on the left and on the right. So I actually don't really even have to check it, although I can check if it's concave up there. So that's with respect to the second derivative. So I can do that if I wanted to. And then in here, at x is equal to 0, I'm pretty sure that that's going to be a local kind of maximum there. So that's going to be concave down, right? So, now so far, this is what we have. And within here on the right-hand side at 4, we've already calculated this. That was our other extreme. So we know that this, kind of really blows up there. So it's all the way goes, somewhere over here. So really we kind of have to be careful here. So this kind of skyrockets, okay, and touches. This is the 0.420. right? So this is how it's going to look like. So this is just kind of blowing up on us over there. And most likely this is going to be joining in like this, right? That's my guess. And then over here, right? So it crosses through that -1 and it still continues on. So it continues on and keeps going. Now I'm going to run out of space, right? But this would have kept going to basically -50. So it looks like this function, pretty much we've sketched it already. Now you can still double check if you want to try to see all the other points that we need. So the other thing is, do we need to create test points to identify where the derivative is positive and negative? So that's what you see right here. So that's very easy to do for us in terms of test points because, here is our derivative. So the derivative on the left, right, of x is equal to 0. So if you substitute, for instance, -1, okay, so if you substitute that in there, so it looks like it is positive, right? So that means it has a positive slope. And then in between 0 and 2, right, so you can substitute, for instance, 1, okay, and for that one, I guess it's going to be negative, okay, so between there, so that means the slope is going to be, coming this way. And then beyond 2, again, it looks like it's going to be positive going that way. So that's you can do those test points if you couldn't see, and that makes sense, right? So there you go, you have it on the left of 0. Okay, it certainly has kind of like a positive slope. On between 0 and 2, it has a negative slope, and then beyond 2, it has, okay, a positive slope back again. Now, the only one thing I guess we're missing, somewhere in between here, so somewhere over here, it looks like we have an inflection point, right, where it changes, because it looks like the derivative kind of goes, in this direction, and then it kind of goes that direction. So it looks like it's concave down, and then it turns to concave up. And that, you may recall, is, the kind of inflection points. I can put up a link up above there if you wanted to learn. Now, how do we know concave up, concave down? That's from the second derivative, right? And that's what you would see over here. So notice number 7, now it says find the inflection points from the second derivative, so setting it equal to 0. And then you can create your test points to see, if it's going to be concave up and concave down. So if I go back in here, now my second derivative, so f second derivative, what will it be? Well, this one's very easy. Right here is to take the derivative. It's going to be 6x minus 6. Okay, so, that's a line. So this is amazing. And now for here, so I'm going to just take that 6 out. So this is x minus 1. If you set this equal to 0, you can clearly see that we have, okay, our derivative equal to 0 at only one point, that x is equal to 1. And that is right here. It looks like it's that point. Okay, so this looks like it's 1, and that's going to be our kind of inflection point. Now, you can still check. So to the left of 1, if you substitute this, so to the left of 1, so you can substitute 0, for instance, in here, you're going to get negative, which means the function is concave down. To the right of 1, you can substitute 2, you're going to get positive, so it's concave up. So that means we have a change from concave down to concave up, and there you go. Now, so that is an inflection point. The other thing is that we were wondering about is, what happens over here, right? Is this really, a local, in this case, maximum? Now, what we would need is, we would need it to be, so basically at 0, we would need it to be concave down, but that's exactly what we just said. If you substitute 0 in here, you're going to get -6, which is concave down. So it confirms for us the function, right, that was a local, okay, in this case, maximum. How about at the other point? So at the other point, at 2, okay, is that concave up? Yes. If you substitute 2 into here, so if you put in 2 into there, you're going to get 6 times 2, 12 minus 6, which is 6. So it's positive. So indeed, it is a local minimum. So a local maximum and a local minimum. And now we basically have a pretty accurate representation of our function. So here's decimals just for completeness sake. Okay, so I know that obviously using decimals, you wouldn't have to do all of this work, you know, but if you wanted to double check for yourself as you're playing and learning how to sketch, then you can certainly do that. Let's see what we're going to get here. So plus 4, and there you go. Now, I guess it was restricted, so we have to put this was between -3, so equal x and then 4. So there you go, that's our restrictions. It's kind of how it looks like. So this point over here, right, all the way down, so notice -50, right, indeed. Okay, the other point, so we had, okay, so whoops, right here, okay, so at 4, it says undefined because, you know, we put less than 4, right? It is true, it's actually not, but notice on the left-hand side, it is 20 on the x-axis. So if I just move it ever so slightly, notice that it's basically approaching 20, right? Which is exactly what we want, but it's not defined there because it's less than 4. Now, everywhere else, you know, so here you go. Here's 0, 4. Here is 2, 0. Notice where it's crosses, -1, 0. So we have, I mean, this is as accurate as we can get. Okay, so this is really, really good in terms of accurately sketching polynomials. So this is one example that we have. Now, I have another example here for you, which is, you know, a little bit tougher. I'm going to try to walk us through this one as well, through this concept. But I'm going to do it in another separate video. Okay, and I'll put up a link up above there, okay, so that you can watch it if you wanted to. Okay, you can start it on your own. So that is the nice introduction. So here are all your steps, things that you can think about, and you can sketch along. So number 8, you can finish your sketch if you wanted. I mean, this is as good as you possibly can make it. All right, so thanks for watching. We'll see you hopefully in future videos. Bye, everybody. Cheers.